So I want to highlight the difference between learning math techniques and ideas and using math techniques and ideas, because you haven't done a lot of the second one yet, or at least I'm guessing that you haven't. So for me, the contrast is like exercises versus playing the game. So in various sports, you learn the basic moves of the game as drills. Like, can you dribble the ball? Can you make the basic shots in badminton? And the idea is you want to break the skills of the game down into the simplest possible actions and then repeat those actions in a very simple, controlled environment so that the steps become automatic for you. So most of the problems that you've done in math class up till now are like that. It's like you only really need to use one idea that you've learned recently, and the problem is created specifically to practice that one idea. It's like a kicking drill. So like all the information that you need is clearly presented right there. You don't need to transform the information. You don't need to fill in any gaps. There's no need to explore any situations at all. It's really clear from the problem what you're intended to do, and all you do is practice doing it. So you saw in the last example that I had where it was the zero product property, like all of these are kind of like kicking drills for the zero product property. They all look pretty much the same as each other, and it's just practicing the idea. So real life is certainly full of exactly that kind of kicking drill skill. It's like you learn a skill, and then what it means to be an expert is you practice that skill in exactly the way that you learned it, and like very little thinking is involved. You're just, a practitioner. But real life is also full of a lot of more complicated problems where you have skills, but it's not really clear what skill fits the situation you have. You don't really know like what information from your current situation is relevant or irrelevant. And that's when you need to do problem solving. So like anytime that you have to do diagnostic things, so if you're a doctor or a car mechanic and there's a problem, you don't know which parts of your knowledge base are relevant or which of your skills you're going to need, because the first step is figuring out more information about the situation that you're in. So in our class, there are math problems that look like that also. They're math problems where you might need to use several different ideas from the course or from previous courses. You might need to transform the information that I give you into a different form so that it looks different before it's clear how it's useful. And you've already seen that a couple of times. I might give you an equation, but it's not really clear what you should do until you think about that same function graphically. Sometimes you need to add into the given information before you have an idea about how to approach the problem, or you might need to explore it a little bit to generate new information. So I want to zoom in on just this aspect. So like, what if you have a problem where you need to add to the given information? Like, what does that mean? What does that look like? So for me, this is kind of a classic Algebra 2 kind of a problem. And why don't you give it a little thought and try it before you watch the rest of the video. So given this circle that's radius 8, how long is that little tiny diagonal line segment that goes from the origin to just touching the circle? So spend a minute and try and solve it and see what you think. So what could we add to this that might make it clearer? One thing we could do is draw horizontal and vertical lines. And once we've done that, you might make a connection. You might say, aha, those green lines are actually the same as the radii of the circle. So you actually know how long they are. And that this base of this triangle is the same as that green line up there. So now you've taken a piece of information that was there in the original problem, the radius, but now it's a little bit clearer how it might be useful. And now you've got another connection. Now that you've got triangles, you know a lot of math that involves right triangles. So you could use the Pythagorean theorem to find the length of that entire diagonal. And then once you've done that, the length of the entire diagonal minus that radius should give you what you're looking for. So that's a solution strategy, thinking if I could find this, then I could do that, and that leads me to my solution. That's the strategy. But if you go back to the original problem, the strategy wasn't obvious just looking at this. So we had to add things to the problem in order for the strategy to become clear. So you could imagine showing this to someone, it's their first day of Algebra 2, and they think, wait a minute, how did you know to do that? How did you know that adding those lines was going to work? And the answer in general, not to this problem, but to all these kinds of problems, is you don't know in advance whether something's going to work. You just have to try it and see. Think about being a doctor or being a mechanic. It's the same situation. You might choose to run a test, and maybe the test will lead you to an important idea or important information about how to fix the problem, and maybe it won't. But like that's the nature of problems you've never seen before. However, there is kind of a deeper thing. You know, as you gain experience as a doctor and a mechanic, you start to gain an intuition about what kinds of tests might be helpful. And so I also have an intuition about this problem. I've done a lot of math problems, and so like I know that I have a lot of math about right triangles. So it was a good guess for me that creating right triangles was going to be helpful because I knew it would connect to other math I knew, and that math might lead me to a solution path. So it was a guess, but it was an inspired guess. It was a guess based on thinking about other things I know and problems I've seen like this in the past. So let's try one more. Here we've got three squares placed next to each other, and the corners A, B, and C here are all in a line. That's what it means to be collinear. So find the dimensions of the largest square. So instead of trying to solve this directly, try and answer this question. What information could you add, or what things could you add to the problem that might let this connect to math that you know, or that might lead to a solution strategy? So for me, they said that these three were in a line, but like how could I take that idea and use it to add more information? So first I could draw the line. And then once I've got a line, I know that lines connects to a lot of math I know. For example, I know lines have slope, and I know that slope is the same as the rise over the run. So you can start making connections here. These things look like slope triangles. So I know that these should have the same slope because they are slope triangles on the same line. So that means the orange divided by this distance of 4 should be the same as this green divided by that distance of 7. So I'm not going to solve the problem the rest of the way. So now I'm starting to get into why are concept maps important. It's like you know a lot of facts about lines, but you needed to have those facts ready on the tip of your mind in order to make the connections that would let you solve this problem. Like you could say collinear and draw the line, but unless you had all of the facts about lines that you know connected in your mind, drawing the line isn't going to help you solve the problem. So for me, that's what a concept map is. The concept map is helping you like make all the connections so that way when you solve more difficult problems, all those connections are there and available to you to use. Because just knowing a whole bunch of isolated facts at the end of the day is not very helpful. So the more associations that you have, the more rich an idea you have about every idea that you learn, the more likely you're going to see aha that lets you apply those to a new situation. And that's ultimately kind of why we're doing all of this. Okay, so you might be thinking, but wait a minute, these are puzzles. These, I heard you say mechanic and doctor and all that, but like these aren't really real life problems. Like nobody is ever going to ask you to find like the collinear points or whatever. So like when would we ever need to do something that unrealistic? The answer is all the time, but like in my life, because I'm a high school teacher, like I'm not an engineer, so I don't do a lot of that stuff. But like I do lead the robotics team. And so a couple years ago on the robotics team, we had this problem where we needed to design a robot that shoots a ball into a goal. And so we designed a robot with a fixed angle shooter, and like it shot the ball with a certain trajectory. But we needed to know, like for our design, what parts of the field was it safe to shoot from or impossible to shoot from or risky to shoot from if we actually had a human driver. And so last year in pre-calc, we spent like probably 2 or 3 weeks working on this problem because it turned out to have a lot of math in it. And I don't want to think about the problem a lot right now, but this is an example of student work from that problem. And what I want you to kind of look at is there's lots of what I was just talking about. There's lots of drawing of diagrams and making connections. People were imposing the idea of, oh, we need to use triangle trig, we need to use circular trig, we need quadratics, we need triangles. And like none of those ideas that you learned last year or the year before, none of those ideas are obvious at all if you look at the question being asked. The question being asked is, what zones of the field are you going to be able to shoot from? So you have to do a whole lot of connecting math that you've learned previously into this new situation in order to sort of answer the everyday human question about where should we shoot from. So crime scene analysis, my college roommate was really into this actually. So like criminal forensics, you can buy whole books where you can like analyze based on the shape the blood splatters in, like where did the blood have to originate from. And same idea here, right? Like there's a lot of triangle trig, sine, cosine, quadratics, all this stuff connects in, but it's up to you to make the connections. So this is like more examples of how your math facts aren't useful by themselves. They're only useful once you can connect them to the question that you care about. So as the year goes on, I'm going to give you more and more opportunities to show off what you can do with the connections that you've made in like real, genuinely difficult problem-solving situations. And what's nice is I'm hoping to do it in a supportive and grade-safe place. So when you do these problems, I am not going to be grading you, at least initially, on your ability to solve the problems. Because when you are working on a difficult problem, there's no guarantee that you'll be able to solve it in any finite period of time. What I am going to be grading you on is, are you able to at least come up with approaches that are good ideas or make sense? Can you connect ideas into the situation? And maybe the ideas you connect are going to be useful and maybe they won't be. But the first step is, can you make the connections? And so that's what we're going to be looking at. There's a famous mathematical saying, problems worthy of attack prove their worth by fighting back. And I've always really loved that. That's really true. I have a collection of problems that I have been working on for many years. I've come up with dozens of different approaches to try and attack them, but they've always resisted my attacks until now. And I still feel optimistic about some of them that I might find an entry point. But I've been doing this for many, many years. And so you're right at the beginning of this journey, if it's one that you're interested in taking. I think that it's a really great way to sharpen your thinking skills, and that your thinking skills are relevant no matter what you want to do. Math aside, you want to be a lawyer, you want to think clearly about how to plan a wedding. All of that requires the same kind of ability to make connections between ideas, to organize information. And this is a particularly nice setting for practicing those skills.